So this talk is about Demigod, a new tool that allows you to analyze kernel rootkits in software emulators. So this project was done by a team of 3 people. My name is Nguyễn Anh Quỳnh. I'm working in Nanyang Technological University of Singapore. I have many interests that include operating system, virtualization, and binary analysis. And I'm the founder and maintainer of few open source reversing frameworks like Capstone Disassembler, Unicorn Emulator, and Keystone Assembler. The next team member is Nguyễn Hồng Quang. He's a researcher at Viettel Cybersecurity. He has some interest in fuzzing and exploitation. The last team member is Đỗ Minh Tuấn. He's a security researcher of SciStack, and he has interest in fuzzing and exploits. Tuấn is a member of a CTF team named Baby PhD, and he made some presentation at Black Hat, USA, Asia, T2, and XCon. So in this talk, we will look into the background, and we present the motivation of this Demigod works. And after that, we introduce how we design, how we implemented Demigod, and how Demigod can emulate kernel rootkits for different platforms, which is Windows, Mac OS, and Linux. We have few demos in our talks. And finally, we introduce some more exciting applications that you can build on top of these frameworks. Okay, first we look at the background and motivation of Demigod. Okay, kernel rootkit. We know that computer system consists of 2 main areas with different privileges. First one is user land, which is ring 3 in x86. The second one is OS kernel, which is ring 0. So kernel function at the lowest level in the system, which has a full control on the whole system. And the malware running inside the kernel is called kernel rootkits. And because kernel rootkit function at the same level with the kernel, it has a full power. So it can defeat all the monitoring and defensive mechanism in the system. Kernel rootkits are very hard to detect and kill because it can have many tricks to evade detection, or it can even kill or fool any anti-malware tools. So when people build the kernel rootkits, they try to make it highly compatible, easy to build, and easy to maintain. So that's why most kernel rootkits come in the form of kernel modules or kernel drivers, which is .sys files on Windows, .kex files on Mac OS, or .ko file on Linux. Okay, so we want to analyze kernel rootkits, which is not easy at all. We set the target that we want to analyze kernel rootkit come into some forms, binary forms, which means we need to analyze .sys files or .kex files or ko files depending on the platforms. So there are 2 ways to analyze kernel rootkits coming in the form of kernel drivers. First way is that we can use dynamic analysis techniques. But this way is pretty troublesome nowadays. To analyze kernel rootkit using dynamic analysis techniques, we need 2 machines, which can be physical machine or virtual machines. So we run one rootkit on one machine, and we run our analysis tool on another machine. And on the second machine, you can run some debugger connect to the machine that running the rootkit. The problem with this solution is that when you analyze the kernel rootkit can crash the machine. And because kernel rootkit function at a very low level in the system, we have very low visibility on the activities of the kernel rootkits. And finally, most of the analysis tools for malware are built for user land, but not for the kernel code. So in fact, we have very few tools that can analyze kernel rootkits nowadays. The second approach is static analysis, which is that you put your kernel rootkit files into some analysis tools like IDA Pro or Binary Ninja or whatever. However, analyzing kernel rootkit in static analysis way like this is also very troublesome. First of all, kernel rootkit can be packed, and in that case, analysis tool, static analysis tool cannot recognize them. And actually, kernel rootkit function depend on the kernel settings, and most of the time, kernel drivers do not have the setting. So, static analysis tools cannot decode and recognize the kernel rootkit very well. And in fact, we try many static analysis tools on kernel rootkits, and most of them have many issues with missing API, recognizing wrongly the kernel structure, and so on. So we think that we need a better tools for kernel rootkits. What if we can analyze kernel rootkit from user land? In that case, we do not have a machine crash issue anymore. We do not need to set up separate machine for analyzing kernel rootkits because everything is in ring tree. And we do not have much risk with kernel level malware. And if everything is in ring tree, we have very good visibility in the kernel activities, into the activities of kernel rootkits. And we can reuse many existing tools to analyze kernel rootkits in ring tree. We also want to analyze kernel rootkits in cross-platform and cross-architecture way sometimes. First of all, it would be very nice if you can analyze Windows kernel rootkits on Linux, and vice versa. We can analyze Linux kernel rootkit on Windows. That would be even better. And we also want to analyze the, first of all, ARM kernel rootkits on x86 machine. And if we can do that, which is very nice. And finally, a better tool for kernel rootkits would allow us to build more and better advanced analysis tool. And would be nice if we can build our next advanced analysis tool in high-level language like Python. So we consider many approach, and we choose emulator approach. So the idea is that we want to emulate OS kernel in software. So we can run kernel drivers, kernel rootkits in emulator mode in the emulators. And because emulator run in ring tree, so if we can emulate the kernel rootkits inside the emulator, we do not have a machine crash anymore. We do not have issue with setting up separate machine or virtual machine to analyze kernel rootkits. And we don't have risk with analyzing kernel rootkits because we emulate everything in the safety sandbox. And we can reuse many existing tools. If you can analyze kernel rootkits inside emulators, we have excellent visibility because you can see all the execution code and you can instrument at various levels. Finally, if you can use some cross-platform and cross-architecture emulator, then you can do cross-platform architecture analysis on the kernel rootkits. And in the case, if the emulator is built in like higher level language like Python, then you can easily build our own tools to analyze many kernel rootkits easily and quickly. Okay, in the next section, we introduce how we design and how we implemented Demigod. So let's look at an existing emulator which is very close to what we are looking for. We are talking about Chilling emulator, which is open source emulator. It supports multiple operating systems. So Chilling can emulate Windows, macOS, Linux. It supports multiple CPU architectures, so it can handle binary code from x86, ARM, ARM64, and MIPS. It's built in Python, open source, and it allows you to perform instrumentation at various levels, at basic block, at instruction level. You can also instrument memory access and so on. Chilling has one very good debugger built-in, which is compatible with GDB Docker, so you can connect many debugger to the emulator to debug emulated code running inside chilling. However, the issue with chilling is that we want to emulate kernel rootkits, but chilling is not built to handle kernel code at all. It can only emulate userland code. So, because the loader for kernel module is very different from the loader for userland binaries, chilling cannot handle kernel drivers at all. Chilling is not made to emulate kernel components, kernel APIs, and the scheme of chilling is quite different. It's built to run the userland code from beginning to end, but kernel module function differently. We need to load the kernel module into the emulator first and let it initialize. And after that, depending on the user input, kernel rootkit will run different code path depending on the input. So it's the scheme of emulating the kernel driver is quite different from the emulating the userland code. So the idea is that we fork chilling emulator and we build Demigod on top of chilling. Because of that, we can reuse many existing nice feature of chilling. So we can reuse loader of chilling with little modification. You can reuse symbol relocation. You can reuse the imported functionalities inside the chilling loaders. But we need to build many of our own tools because chilling do not have those features. For example, we need to emulate the kernel components ourselves. Demigod also need to emulate kernel APIs by hooking and emulating this, emulate on the kernel API semantics. And we also had to do our own instrumentation for the kernel rootkits to work. We need to hook and emulate system kernel API. And for debugging, this is good because we can reuse the existing GDB server built-in inside chilling. So Demigod can enable the GDB server when you emulate the kernel rootkits, so we can debug the kernel rootkits running inside the chilling. So here, I want to emphasize one thing that makes Demigod different from the chilling. The userland code is typically only one phase emulation. This is what chilling does. But for Demigod, we need to emulate the kernel rootkits in two phases. First, we need to load the kernel driver first, and after that, the kernel drivers or kernel rootkits stay inside the Demigod emulator and wait for the request from the users. So you have to emulate the driver entries. For that, we need to locate the entry to emulate. So for Windows, we need to locate the driver entry inside the .sys files. For macOS, we need to locate real main symbol inside the .kex files. For Linux, .ko files, we need to locate module init. So after that, we can start emulation from the driver entry. But during this phase, we need to monitor and check on the code path that we can see when the kernel rootkit was initialized. So first of all, we want to check out the rootkit system calls because rootkit can override some system call inside the system. We need to retrieve the I/O control callbacks and many other register callbacks that depend on the platforms. And the next phase, the second phase, is that once we get all the callbacks on the code path that we want to explore, we try to emulate the code path that user choose to explore. So at this phase, user can decide which code path they want to emulate, and by doing that, they choose the input and they send the input to this code path, and Demigod can emulate this code path with this input coming from users. So building Demigod is very challenging because emulate kernel is very tough. There have so many complicated software components inside the kernel, but we choose to limit our implementation. We only emulate enough to make rootkit work. And building the loader for kernel driver is also very hard because it's quite different from chilling, what chilling does. And how to initialize driver is also not easy, not trivial. And during the driver initialization, we need to extract the code path to be emulated. And after that, how to trigger the code path with properly formatted input from users is also another task we need to consider. So in the next section, I will hand over to Mr. Quang, who will introduce how we implemented Windows emulator for Windows kernel rootkits.
Hello, my name is Quang. Today I will introduce about Demigod framework. I use Demigod to emulate Windows driver. There are many things in Windows kernel that we should consider. The most important thing is anti-OS kernel. The file is known as kernel image of Microsoft Windows. Windows kernel contains many components such as cache manager, memory manager, and scheduler. To emulate Windows driver, we have to understand kernel structures, kernel API functions, and write code to copy or mimic the behaviors of Windows kernel. I load driver module into emulator and start emulating from the entry point. I also instrument memory access and code execution by using hooking technique. After initialization is complete, I use I/O control code to communicate with driver. Every driver is a key file and the subsystem field of optional header equal 1. So that I have to read the header, file section, and write them into memory of emulator. I also load dependent library, resource import and write table. After that, I check relocation table to relocate every address. The second step is setting up CPU context. We should set up stack pointer with point to stack location, RIP point to entry point, and control register. Some driver will not work if CR4 register and CR8 register are not set. The third step is initializing some important structures such as driver object, process, and the last one I prepare for driver entry. It is the first driver callback and is used to initialize the driver. Now I will introduce some internal structure. The first one is driver object, represents the image of loaded driver. I initialize some things such as type, size, driver name, and major function field. Process represents a process object. There are many hidden fields. I just allocate a memory region for this structure. Key user share data is the data structure used between user mode and kernel mode component. IRP structure represents an I/O request packet. I/O stack location is an entry in I/O stack and associated with each IRP. MDL is a structure that represents memory register list. Driver entry is the first function that used to initialize driver. This function is often called an entry point. The first argument is a pointer to a driver object structure, and the second one is a pointer to Unicode string structure that specifies a path to driver parameter key in registry. I also write some hook API to mimic Windows API. I implement hook function to emulate API and make everything work. For example, IO create device will create a fake object in memory of emulator to represent device object. IO complete request do nothing but log on the parameter. Some memory management functions such as xallocate pool, xfree pool work similar as malloc and free. After everything is ready, user space program can communicate with driver via I/O control code or read file and write file. I create structure IRP I/O stack location in memory emulator. I find a structure with appropriate data, set up arguments for callback function, and I start emulating from the beginning function. When everything is complete, I determine return value and return data by reading IRP structure from emulator memory. There are three methods to communicate with driver. The first method is buffer I/O. So I create a large enough buffer and assign and wrap of this buffer to IRP system buffer. The second method is direct I/O. I create a buffer to store data and create a MDL structure for this buffer. And the last one, neither I/O. I just set user buffer field of IRP structure point to address of this buffer. I also create two tools for reverser. The first tool is a tool to unpack kernel mode packer, and the second one is a tool to help when working with I/O control code. Now we will watch some demonstration. The first demo, I will debug a Windows driver. You see here, I enable debug mode by adding the following line. And now I start to emulate driver. There are driver object, registry, ePOSET, and user share data are created. When everything is done, the driver is ready. I use IDA Pro to connect to the port 9999. And after that, I can use IDA Debugger to check every instruction. And you can see this driver print to console hello world. And done. The second demonstration, I want to introduce about malware. It is Sality malware. You know, Sality is a polymorphic file vector. It communicates over a peer-to-peer network to form a botnet. Sality uses a rootkit to block connection and kill antivirus process. I found a sample from VirusTotal and I will debug Rootkit from Sality malware. I have searched and found a variant of Sality from VirusTotal. There are 64 engines that detect this file. At first, I have to extract the main module from Sality. Sality uses zip module to extract rootkit and load rootkit into memory. This user mode module is a dynamic link library and I name it sality.bin. I use Sality extractor. This is a script that I wrote from another research. After dumping the DLL, I unpack by using UPX engine. And then I load this module into Emulator. And now you can see Sality execute inside Emulator. There are too many instructions. Emulator speed will spend much time to execute. Now you see this is a Solidity malware create a service. Here is name. We have a service name and the binary path. This is Rootkit module of Solidity. I will use IDE Pro Debugger to connect and debug it. I can step every instruction. Solidity malware communicate with driver by using Wi-Fi function. And the Rootkit had two threads. The first thread will block all antivirus related connection, and the second one is to kill process. I will separate by as this thread to debug later. Solidity will find anti-terminate process from user mode by using service descriptor table and send an array of address to kernel module. Here you see Solidity QR process with the number with our PID number. That was my demonstration. And next, Mr. Tuấn will talk about how Demigod work on Mac OS X. Thank you.
Hello, I'm Tuấn, and I'm gonna talk about the mechanism of Demigod for Mac OS. So the Mac OS kernel is officially known as XNU, and it is a hybrid kernel which combined from Mach kernel and BSD kernel. It also brings the format of Mach-O executable file. The kernel exposes its interface, as known as KPI, to let the user use its functionality, and all of them are implemented inside the kernel code. Like other OS, macOS needs drivers to control devices. They are called as Kernel Extension or KEX. The kernel extension is a bundle of files, and the kernel loads it from external space. Some interesting information can be gathered from info.plist inside the bundle. Our goal is to emulate on code path of a rootkit in the case. So in order to emulate driver, I decided to load both kernel and kernel extension together. Because the kernel is also a Mach-O executable binary, as well as the main component of the case, so I can load all of the segment 64 to Emulator engine. Now I have implemented code of all KPIs from the kernel. Besides, like a normal application, I have to resolve local symbols and some other dynamic symbols of the case. However, the kernel releases its KPIs through some dependencies, so it is necessary to create a jump code as a kind of indirection calling. Next, a driver will run from its initial function, and this entry address can be extracted from binary symbol. For IOKit driver is start method, and for generic driver is an address stored in real main symbol. Before emulating driver, I should initialize kernel environment. I set up MAC policy list by allocating new object in Emulator engine and fill that address in the target on kernel space. The same thing I will do for onProc symbol on kernel space. I also create some vnodes and credential. Then I run emulation for pre-process such as attack, probe, or kmode info. Finally, I can go into the entry of driver. Speaking about the instrumentation, I map all KPIs which was exported from kernel to user-defined methods. It helps to simplify some features, or we can pass through it and use native function. On the other hand, I also hook KPIs to disable multi-thread functionality. And for some unrelated to host environment function, I give driver a chance to interact with a real machine. For example, get attribute list box is a function to retrieve every entries in a directory. So I just scan all the files and folders in directory and pack them using VFS attribute pack function from the kernel. About the syscall emulation, I just find the sysend symbol on loaded kernel space, assign the arguments to register, and run the entry address. In some cases, we want to call a native KPI from a hook KPI. Normally, we have to save the current state and run another emulator, but it may screw up when in some complicated situations. So I construct a junk code and push its address to stack as a safe RIP. This junk code has three main missions: prepare arguments to register or stack, clear stack after calling, and jump to native KPI directly. Under the kernel, there are many events and callbacks need to be emulated. So I built an event management system to listen a register request from driver and emulate the interaction from user. So this will make macOS from asynchronous system to synchronous system. I use EMS for sysctl event, NKE event, some network filter, MAC policy callbacks, and chaos features. So in order to show how our tool works, I will use Demigod to analyze one of the famous rootkits on macOS, Rubelin. It was released full disclosure in 2012. It can give root to a running process, hide file or folder, etc. Also, it couldn't run on modern kernel due to some reason, such as memory arrangement, KPI change, read-only syscall table. So to upgrade this rootkit, I use save RIP from an initial function and step back to find the kernel base. Then I scan all the memories to find the sequence of syscall handler to determine the syscall table. Moreover, I modify the CR0 register to override entries in syscall table. So here is the demo for running rootkit on the real machine. First, I load the driver and run an agent on user space. From this UI, I can command the Rubelin easily. Like high up running process, or hide file in current directory. Or even remote code execution through an ICMP packet. Here I will start the calculator application. To emulate Rubelin, I load it and run its initial function. Then it will automatically register some callbacks to my EMS. I also build some default objects like a network, sysctl arguments, and fake processes. Here is the demo. Now user can pass his input to some rootkit features, like grant root permission to a process, hide a process, hide a file whose name is to do and Kernel LS application. Then I can trigger the backdoor through ping command. Especially, we can also debug this rootkit by enabling GDB feature of Demigod. This video will demonstrate the debugger. First, I will disassemble all the instructions that rootkit has went through to get the address I want to set breakpoint. Then I start the GDB server and connect to it from GDB client. Now I can step in. Step. Set a breakpoint. Continue. Set a file breakpoint. Continue. Dump register. Next, Mr. Quinn will show how Demigod works on Linux.
Okay, so in this session, I introduce how Demigod support Linux kernel. So we can analyze the kernel, Linux kernel rootkits inside Demigod. So Linux kernel is actually a very complicated system with many subsystems. But for Demigod, we only look at some relevant subsystems that are enough to make kernel rootkit work. The first one is system call, because system call play a very important role to provide services, and many kernel rootkits would override the system call to provide their own functionalities. And we also care about the I/O control system call, because the kernel rootkit can provide some functionality to the user land via this system call. And there's also some other callbacks that can indirectly trigger by the user land that we also need to emulate their, for example, like file operations. And because kernel rootkit in Linux is built as Linux kernel module in .ko format, so we need to support the .ko format, which is EAF format, but a bit different from the user land. So the goal is that we try to emulate kernel rootkit in .ko files. So for the loader of Demigod, for the .ko files, we need to build our own loader, which is quite different from the loader of Chilling. So we need to pass on the section of EF files and map the on the section into the emulator memory. And Demigod also need to resolve on the external APIs, so we can provide our own implementation in the emulator. And finally, we need to relocate the external function and symbol data. The next thing Demigod had to do is that we need to set up the CPU context so the kernel rootkit can function properly. And one of them is that we need to set up a GS segment for current task, because many kernel rootkit try to access to the current task, and they need GS segment for this. We also need to initialize system call table of Linux kernel, so the kernel rootkit can access, can read, can write to the system call table. So for this part, we had to write the arrest of our own system call implementation into the system call table, and we had to hook the system calls. So when the rootkit access to the system call, we can execute our own system call implementation. Finally, for the loader, we had to locate the initialized function of the .ko file, which is an init module symbol. To support Linux kernel rootkits, we had to emulate many Linux structures like task struct for the userland task, file operation, because the rootkit can modify the file operation, so it can trigger the callback to the file operation like read, write, open, and close. We have to support the module structures because the kernel rootkit can access to the list of modules inside the system and modify something like, for example, they try to hide some kernel modules. So they have to read and write to the list of the modules, and we have to support that as well. The few other structures we have to support like user namespace. So the kernel rootkit can modify the user credential. We have to support file structures because kernel rootkit can modify the file structure, and some other structures like Linux DRAM. So this is necessary because some kernel rootkit can try to modify and hide some directories. Okay, so we Demigod have to emulate the .ko file initialization, and because when the kernel rootkit, when the hacker loads the kernel rootkit into the system, they can specify some optional arguments. So for the Demigod to work properly, we have to do the same thing. So we also need to support optional arguments for the .ko files. And okay, at this phase, user need to specify the input for the init module entries. And after that, Demigod can start to emulate from the init module symbols. Okay, we have to hook many Linux kernel APIs for the rootkit to work properly. And here I list some of the most important APIs inside Linux kernel. So here's some API for function initialization, for memory access, for memory management, heap memory management, for device management, and some system calls. We have to hook and we need to emulate some system call as well. Okay, once we can extract all the code part we care about during the kernel rootkit init phase, we can emulate them. So for example, you can, during the init phase, Demigod can extract the system code because kernel rootkit can override some system code, so we need to get them out. And also we need to get all the callbacks that can be registered by the kernel rootkits. And after that, we need to trigger the code path the code path that user want to emulate. So at this phase, user can decide the input requirements for the code path that they decide to emulate. And yeah, here I list some of the most popular code path that Kernel Rootkit can set up, and user need to specify the input for all those code paths if you want to emulate them. Okay, next I have a little demo for Linux. So you can see how we can use Demigod to analyze a kernel rootkit in Linux. And in this case, we look at the kernel rootkit named Mohammed. And this one is a very typical kernel rootkit with many typical behaviors. For example, Mohammed rootkit can try to hide kernel modules, it can hide files, it can hide network ports, it can grant root access to current process, and this rootkit actually override many system calls. And it can also interface with user LAN via some using some customized files in /proc file system. And actually, you can find the source code of this kernel rootkit on GitHub. So in this demo, we try to emulate this kernel rootkit, and to do that, Demigod will load the rootkit into the memory, initialize it, and we try to extract the new system call made by the rootkit for the right system call. And in the demo, we emulate this right system call directly with some selected input, and we chase all the activities of this rootkit with the debugger IDE. So here I have the video demo. Okay, so here you can see that I have a kernel rootkit in the file name rootkit.ko, and Demigod is going to emulate this rootkit.ko files. So you can see that on the screen you have two windows, the console on the left side, in which Demigod will emulate the kernel rootkit. On the right side, you run IDE Pro, and IDE Pro will be used as a debugger, and we will connect this debugger to the kernel rootkit running on the left side on the console. Okay, so here you can see that on the left side, when I run the kernel rootkit in Demigod emulator, the rootkit will stop and it open a GDB interface at the local host address at the port 9999, and it's going to wait for the debugger to connect to. So we run the IDE Pro debugger on the right side, and we set up the IDE Pro to connect to localhost at the port 9999. Okay, see here you can see that I try to attach IDE Pro to the GDB debugger inside the emulator on the left side. Okay, you can see here that once we connect the debugger, IDE Pro will put a breakpoint as the initialize function of the kernel rootkit, and you can see that in the IDE Pro window, you can see the code of the debugger. You see the code of the rootkit. So now I will set a breakpoint on the first instruction, which is the call instruction, and you can see that we can use the debugger like normal debugger instruction with the user line code, but you can see that you can debug kernel code. So here on the right side, I do some single step. And on the left side, you see that the kernel actually runs. And you can compare the left side, the right side, you see this actually exactly the same thing. The same instruction get executed. But you can see the difference is that on the right side, at this arrest, in the IDE Pro, you can only see the call some unknown function. But on the left side, because we actually emulate the kernel rootkit, you can see that this call actually is a print k function. And at this place, actually the kernel rootkit print out a message which is module starting. So you can see that on the right side, IDE Pro doesn't see much, but on the left side, because we actually emulate the kernel, you can see a lot more information. Okay, so I continue to single step inside the debugger, so you can see how the kernel rootkit executes. Yeah, you see here on the right side, IDE Pro doesn't see much, but on the left side, we see many more information. Like for example, you see here that you can see on the left side that based on some message, you can see the rootkit already initialized some proc file system. Okay, here you can see that the initialized phase of the rootkit is already done, and IDE Pro doesn't see much, but Demigod can see that this rootkit modified four system calls: read, write, open, and close. So the next phase is that we decide that we want to explore the write system call made by the rootkit to see what this one does. So we just continue to chase in the debugger. So on the left side, actually, for the Demigod to work, we specify some special input for the write system call. And here you can see that on the left side, you can see that the rootkit already make the current process root. And after this write system call finished, the current process become root. That's what this rootkit does. Okay, that's how the rootkit works, and you can see that very clearly inside the demo. Okay, so actually you can see that Demigod can emulate the kernel rootkits, but more than that, you can build many more applications on the Demigod framework. So you can debug kernel rootkits inside ring tree, like what I already showed. You can build auto unpacker for kernel code. So in that, you can chase code inside the kernel rootkit to detect the time the code is unpacked. Then you dump and you can auto rebuild the binaries. You can build I/O control analyzer, so you can automatically discover all the I/O control code with different input, and you can exchange the callbacks of I/O control code. You can also build the auto-summarize rootkit behavior to produce high-level reports. So this idea is that you can build, you can automatically discover different rootkit paths with different random inputs, and after that, we can build a summarized report for all the behaviors. We can see when the rootkit execute with different input on different code paths. And the idea is that It's quite easy to do that because Demigod enable save execution on checkpoints. You can take snapshot and reverse. And there are many other exciting ideas that are waiting for you to explore. So regarding the status and future works for Demigod, Demigod now already supported Windows, Mac OS, and Linux kernel rootkits, but there's still a lot more work in the future. We still need to test and to improve Demigod to support more rootkits. So we need to handle more kernel APIs, more system calls, more kernel subsystem. And maybe you can look forward to supporting more platforms besides Windows, macOS, and Linux kernel, like iOS or Android. And we plan to merge Demigod into the chilling emulator very soon. Okay, here comes my conclusion. Demigod is a framework to emulate the kernel rootkits, so you can analyze ring 0 code from ring 3 in safety box of the emulators. So you can monitor, you can chase, you can debug, and you can do on-cap dynamic analysis with Demigod. Demigod was built on top of the excellent chilling emulators. So it supports multi-platforms, multi-architectures. Demigod enables advanced binary analysis on top of the kernel code, and they allow you to use Python language to build your analysis tools. And it supports many kind of instrumentation, so you can easily analyze the kernel rootkits running inside Demigod. So we plan to release the full source code of Demigod very soon, and we plan to merge Demigod into the chilling emulator very soon. Okay, now Q&A session.